Okay, so here's a few things from section 7.9. We had improper integrals with infinite limits of integration. And so we had a definition or that the definite integral from a to infinity of f of x with respect to x, we could, instead of having infinity up here, which is an improper integral, we could have a b up here and then take the limit as b approaches infinity from a to b of f of x dx. So if this limit exists, then to a specific number, then this is going to be a convergent improper integral. If this limit is infinity, then this limit doesn't exist, then this would be a divergent improper integral. Similarly, if we got a minus infinity on the bottom to b of f of x with respect to x, assuming f of x is an integrable function, we can take the limit as a approaches negative infinity from a to b of f of x with respect to x. If this limit exists, then to a specific number, then this is a convergent definite integral. And then last but not least, if we go from minus infinity to infinity, which is another improper integral type with infinite limits of integration, we can pick any number in between, which really any number, because there's infinitely many of them. But we just pick some c so we can split it up just like we did before. Limit as a goes to minus infinity from a to c of f of x dx plus limit as b goes to infinity c to b of f of x dx. If both of these limits exist to a specific number, we can add those together. Then that would mean this limit exists and is convergent. Otherwise, if either one of these is infinite, plus or minus infinity, or doesn't exist, then this is going to be a divergent integral here. So anyway, this c, a lot of times, since it can be any number, really, in between, we're just going to use 0 a lot. That's just an easy number typically to use and plug into different functions. So let's look at a couple examples on this, and we'll do number 14, which was not to be turned in, but it's a nice improper integral with an infinite limit there. So number 14 was integral from minus infinity to infinity of x e to the minus x squared dx. Okay, so first we're going to have to use that last version. I'm going to go to 0. So I'm going to rewrite this as the limit as a goes to negative infinity of definite integral from a to 0 of x e to the minus x squared dx plus, sorry, I got to do the limit as b goes to infinity, definite integral 0 to b of x e to the minus x squared dx. Okay, so we have to evaluate both of these. If both limits exist, then it's going to be a convergent improper integral with infinite limits. If either one of these does not exist or is infinite, plus or minus infinity, then this would be a divergent improper integral with infinite limits. So the way we do this is going to be easiest to say, hey, let's let u, instead of e to an awkward function, we're going to just let it be e to the u. So let u equal minus x squared, and then du is going to be minus 2x dx. Notice that we have x dx that I can plug in there and replace that with du over minus 2. Okay, so instead of doing, we don't know from a to b or a to 0, I don't know what it is, right? Because now I'm changing it over to u, so I'm just going to leave those off, and it's going to be minus 1/2, and I have a du, and that replaces the x dx, and instead of e to that minus x squared, it's going to be e to the u. So this is pretty easy to take an antiderivative of. Antiderivative of e to the u is e to the u. So this is minus 1/2 e to the u power, okay, which if I back substitute it, it's going to be minus 1/2 e to the minus x squared power. And then I'm going to evaluate this That's what this one is. And I'm going to evaluate this from A to 0 for the first one. And then I'm going to take the limit as A goes to negative infinity. So let's go ahead and plug this in from A to 0. I'm gonna come over here now just for this left one. So this is -1/2. So when I plug in the top side, I'm going to plug in 0 for x. And so it's -1/2 e to the 0 power, which is just 1, right? And then minus, I'm going to plug this one in. I'm going to keep that -1/2 out front, and I'm just going to plug it into e to the minus x squared. So it's e to the 0 minus e to the minus a power, right? Minus a squared power, because I got to square that a, right? I'm good with that. So with this, we know this is -1/2. I'm going to rewrite that. E to the 0 power is 1, and then minus e to the minus a squared, I'm going to write as 1 over e to the a squared power. So I'm going to get rid of that negative exponent, make life a little easier. I could have done this here. I could have rewrote this as x over e to the positive x squared if you wanted. Doesn't really matter. But anyway, this is what I get for this definite integral from a to 0. I'm going to get this. And then what do I need to do now? I need to take the limit as a approaches negative infinity, right? So if I take the limit as a approaches negative infinity of this, what do I get? Well, this is going to be limit of the constant is a constant. But anyway, so it's -1/2 times 1 minus, and then what happens here? This 1 over, if I've got minus infinity and I square it as positive infinity, it's 1 over e to the positive infinity. So, which is 1 over infinity. Of course, that goes to 0. So the 1 over e to the a squared, if you'd rather just put it there, that goes to 0 is fine. So this equals 1/2 on the left side. So this left definite integral is, improper integral is convergent. This limit is convergent. It exists to a specific number. So this particular one is convergent to 1/2. And then what we need to do is we need to figure out the other side. Well, the other side is going to be evaluated in a very similar way. I'm going to use green for this one. And remember, we're going to add these together. But on the right side, I end up letting u equal minus x squared. I can do the same substitution methods. And I'm going to get the exact same thing for when I back substitute of -1/2 e to the minus x squared. But in this case, I'm going to evaluate it from 0 to b. Actually, I'm just doing this part right now. Then I'll take the limit. So 0 to b, when I plug in 0 to b, now it does flip it. And so it's -1/2. I'm going to keep that out front. When I plug in b, it's e to the minus b squared, and then minus plugging in 0, e to the 0 power. So instead of the 1 being at the beginning of the binomial with the minus sign in between, it's at the end. So anyway, this is 1. So this part becomes -1/2, 1 over e to the b squared, if I want to make that a positive power, and then -1. Okay, and then that's what I have for the definite integral. And then now I can take the limit as b goes to infinity of that. And when I take the limit as b goes to infinity of that, let me erase this down here. What do I get? I'm going to get -1/2. B going to infinity is 1 over e to the infinity. 1 over a huge number goes to 0. So this is 0 minus 1. So this ends up being a -1/2 times a -1 is a +1/2, right? So that's what I get for that limit. So this is also convergent. So both of these are convergent to 1/2. And then, of course, what am I doing in between? I'm taking 1/2 plus 1/2. And so this improper integral with infinite limits from negative infinity to infinity of x e to the minus x squared dx is convergent to 1. So remember, it's like area under a curve extending out both ways forever between the function and the x-axis, right? So if everything's on or above, it's like the true area. If it's negatives, it would cancel.
Should it be negative on half, the bottom one?
It should be negative a half. Let's see. Thank you. Yeah. So let's see. So it's not 1 because this is minus a half times that. Yeah. This is. Let's make that correction in red, which is what I do on tests, right? So minus a half for me for missing that sign. Minus a half plus this one's still positive though, right? So that actually ends up being 0. And I might say, well, is that the true area? Well, what happens here as you expand out to infinity, you've got stuff above the x-axis that's exactly the same as stuff below the x-axis, and they cancel each other out. So this would not be the true area, but it would be the integral from negative infinity to infinity. Yeah, so that one should be 0. Let me just double check. Yep. So yeah, 0 was the answer I was going for, not 1. So my bad on that. So I'd probably, on a test, I got to take off a point for that. If this is a 10-point problem, you're probably only going to miss 1. If it was homework, you're probably going to miss a half. Because I'm pretty friendly on the grading scheme. So that's but either way, it's still convergent though, right? So it's a convergent improper integral with infinite limits. All right, so let's look at one that's divergent and see if there's a, besides actually calculating it out and getting infinity, I'm gonna show you something here that could help you recognize. So number 17, I've got the integral of the natural log of x with respect to x, and we've got that going from 1 to infinity. So we got to be careful where we're going from. Because I can't have a negative number here because I wouldn't be defined for the natural log, right? I'd have to have natural log of the absolute value of x or something like that. But anyway, so natural log looks like this. At 1, natural log of 1 is 0. And then I'm going out here like that. So once again, I don't have left of 1 there. But really what we're trying to do, if you think about it, the concept of this is we're trying to find this area underneath the natural log curve from 1 all the way to infinity. So, we could say by definition, we could replace that with a b, limit as b goes to infinity of 1 to b of natural log of x dx. But this is going to be divergent because what happens is we don't need to do too much work on this. The limit as x goes to infinity of the natural log of x, well, what happens to the natural log of x? It keeps going out and up forever, right? So it's going to get bigger and bigger and bigger. So there's no way that we're going to be able to capture all that area. We don't have anything negative that's going to offset this as we go. So this equals positive infinity. So basically, we're going to be, even if we rewrote that, the limit as b goes to infinity, this is what we would normally do, natural log of x dx, right? So even if that's some specific number, that's going to continue to get bigger and bigger and bigger and bigger. And because the limit as x approaches infinity and natural log x is plus infinity, that's going to mean that this improper integral with an infinite limit is going to be divergent. So really didn't even need to work anything out or know what that definite integral is or things of that nature. All right, otherwise, if we do work and we get an infinity answer, plus or minus infinity for an answer, then that limit doesn't exist, and your improper integral with an infinite limit would also be divergent. Thanks.